There's a special class of motion in 2 dimensions known as circular motion. And hopefully this is something you did as a kid. You picked up some weight on a string, maybe some keys on a lanyard, and you started spinning it around like this. And I think what you found out was that the harder you spun, the more it pulled. So how fast it's going must have some effect on the force that we're studying. In this lab experiment, you're going to try to figure out what that relationship is. You're not going to do something like this Angry Bird. You're going to use this 200-gram weight. And instead of spinning it in a circle, you're going to give it a little pull and let it move back and forth. The arc it's tracing out is part of a circle, and the motion at any given time will be like that in a circle, but it's a little bit easier to control. We know there must be some forces involved. We know that because the weight has an initial velocity. It's an object in motion, so according to Newton's first law, or the law of inertia, it should stay in motion and keep going like that. Of course, what it actually does is move in a circular path. So we know there's forces. And of course there's forces. There's strings and things like that involved. What are the forces? Clearly there's gravity. And there's an upward tension due to the string. If we were going to do our usual 2-dimensional force problem, we would write sigma F equals ma. That would turn into our upward tension force minus our downward gravity force equals ma. And I think you can see there's nothing in this equation that has anything yet to do with velocity. Got our tension, our gravity. This acceleration term, though, we don't really know anything about it. We know there's an acceleration because the object does not continue in a straight line. But maybe it's this term, this a, maybe it has some relationship to velocity. That's what we're going to try to find out in this lab. So we're going to measure the velocity of our weight as it passes through the point where those are the forces on it. We're going to vary that velocity, and we're going to see what effect that has on the forces. And hopefully that gives us some idea of the relationship between force and velocity. For our circular motion lab, we're going to use automatic data collection so that we can figure out what the forces and velocities are on an object at an instant. The object we're going to be interested in is this hanging weight, which is passing through a photo gate. And we're going to give a little tug to our weight and let it go back and forth. So it's in an arc, and at any given time we could treat that as it being in circular motion. The photo gate is going to help us figure out speed, and then we've got it hanging from a force sensor, which is going to help us figure out what forces must be on this weight. Beautiful thing about this is, although this computer here is quite old, it will do automatic data collection, and it will get us information we need for speed and for force at exactly the same time. So here's how the experimental procedure goes down. When you first get here, you're going to lift the weight up so it's not hanging down. I can't do it because I don't have enough hands, but there's a button on the side here that says push to tear. While you're holding the weight up, you're going to tear that. That sets the force sensor to 0. So I'll do that real quick. We're then going to hold off to the side, and you're going to do it from a variety of different heights, being careful not to tug on it. And you're just essentially going to let it go. Now, before you let it go, you're going to start the automatic data collection on the computer. So we'll hit start and then let it go. Just let it go back and forth 3 or 4 times. You can see the force sensor records continuously, and the photo gate gives specific data points. So once you've got a few, you can hit stop. So what we want to do here is match up times that the photo gate was telling us was important and what the force probe's saying. Now, this right here, time, is not data we really care about, but it's going to help us do the matching. So we'll ignore the first one, but it looks like at 0.843 seconds, we were in the photo gate for a very short time. So we'll go over here and we'll look for 0.843, so that's between 8 and 9. We can see that that's when the force was actually at its maximum value. So we're going to record that. And we'll record the elapsed time, which was actually this value here, 0.0829. We'll leave velocity blank, we'll calculate that later. Same with sigma f. And then whatever the force probe said at that time, which in this case between 0.8 and 0.9 was minus 2.01, we'll record that there. And we can just leave the minus off, so we'll say 2.01. You're then going to repeat the experiment for a bunch of different drops, 10 in all. In order to make it not get too messy over here, between runs, on this old computer, we're not going to be saving any data. You can go to Experiment, Delete All Data Runs. It'll get mad at you. You got your 1990s little clip art guy here, but yes, it should. And then you're ready to go again. Just drop it from a slightly different height.
The faster one moves, the more inward force we need. Here's our setup. We've got our force probe. There's an upward tension force and a downward gravitational force. So the net force here, the combination of these two forces, that's what's actually providing the inward acceleration. They do it together since there's more than one. So what I want to do in this lab is I want to make a graph on how net force, how hard is having to be pulled inward, is related to velocity. Now, of course, sigma f is also equal to ma. So if we have ft minus fg equals ma, there's no velocity in this equation. So this a that we're looking at, we have not studied that yet, and it must have something to do with the velocity, just based on our idea that the faster we spin something in a circle, the harder the tug is. Again, these two forces together are going to provide the centripetal acceleration. They're going to provide the inward pull. And we're just expecting that that acceleration has something to do with velocity. If you graph the tension force from the force probe versus time, you get this interesting sinusoidal graph. And the two force pictures to the right explain it to us. When the weight is fully down, tension is opposing gravity, and the two of them together are providing the centripetal inward acceleration. When the weight's off to the side, gravity's still pointing down, so tension's not completely opposing it at this point. So that will require less force. So since we're only interested in the weight when it's at the bottom, we just have to look for where on the graph we're at maximum force. That's the place we're going to record the tension from.
The photo gate doesn't know how fast the weight's going. It just knows how long the beam of light between its two horns is blocked. So you can imagine that if this was a bigger weight, bigger like in terms of shape, it would block the photo gate for longer, even if it was going the same speed.
So here's our weight swinging through the photo gate. As we said before, the photo gate just records the amount of time it's blocked for as the weight swings through. To get that into a velocity, we have to use the equation velocity is change in distance over change in time. The change in time is obvious. How long is the photo gate blocked for? But I think you can imagine if this was a fat weight, it would block the photo gate for longer. If it was a skinny weight, it would block it for less time. So the delta x in this question is actually the width of the object. This device you have here is called calipers. It's good for getting the diameter of things. There's these teeth which you spread out, put around your thing and clamp on them. And then you can read off the scale how wide apart the teeth are. So this thing has a diameter of 3.5 centimeters. So again, the goal is to see the dependence of force on velocity. We're going to get that from this graph. And the equation that's going to get us there is our sigma FR equation. The force probe gives us the tension force. We have to account for gravity. We'll get that just from what the force probe said when it was hanging still. And we expect velocity to have something to do with acceleration. So you could see the left side of this equation is kind of like y, and y equals mx plus b. The right side is going to kind of be like x, because velocity we expect to be something in that acceleration term. So the first step, once you have all your data in a spreadsheet, notice I have elapsed time here and tension force here, is to calculate your velocities. So velocity is distance divided by time. So my width was 3.5 centimeters or 0.035 meters. So in this column I'm doing equals 0.035 divided by the time. In this case B4, because that's the location of my first time. I'll hit enter and then I'll click and drag down and I'll have all my velocities. We have to remember that the force probe was registering tension, but what we're interested in here is the net force, sigma F. So to get that, we have to take our tension force and we have to subtract the force of gravity from it, according to the sigma F equation. So that's why we got the weight of the mass when it was just hanging down. My tension forces are in column E, so the formula is equals E4 minus the measured weight of 1.92. Click and drag down, I should have all my sigma F's. So I did a graph of velocity versus sigma F, and I first put a linear fit onto it. It's not terrible, there's a lot of error, but it looks like there could be some bowing here in the middle. We have stuff that's over at the ends and under in the middle. So let's try a curved fit. The curved fit is slightly more convincing. I did a quadratic fit here. So in other words, we're saying sigma F is proportional to some number times v squared. I'll give you that the data is not high enough quality to totally say that, but that is what we expected, and it does seem to be slightly better. So I'm going to operate from now on with the assumption that sigma F is proportional to v squared. The data we just saw seems to suggest that sigma F is proportional to v squared. Now, we know that sigma F also equals ma, and we were saying that this v dependence is probably hidden somewhere in the acceleration. So I'm going to make the second claim that sigma F is proportional to mv squared, because the m in sigma F equals ma. So to make that proportionality into an equal sign, we need to multiply by some constant. So that's where the last one comes from. Sigma F is kmv squared. So we should probably try to figure out what that constant is. And I think using dimensional analysis, we can do so. So let's use the trick of dimensional analysis to try to figure out what this unknown k is. In the center I've got sigma F equals ma, and I've put the units below that equation, color-coded. And we can see that the Newton, according to this equation, must be equal to the kilogram times meter per second squared. So on the right I've taken the tentative equation we have, and I've plugged in all the units we know. So in that second to last line we have the kilogram times meter over second squared equals something times kilogram times meter squared over second squared. So there's an extra meter on top there. So that means the pink term must have the units of 1 divided by meter, 1 divided by some distance. So
what's the only distance that seems relevant for circular motion? The distance that's the radius.
Guessing that the only relevant distance was the length of the string, we're going to see if our experimental data fits this idea that the constant k could be 1 over the length of the string. On the quadratic graph that we saw before, we had sigma f equals some number times v squared, and just from the graph that number is 0.5. So 0.5, if we go by that sigma f equation up top there, 0.5 has to equal km. So I plugged in 0.5, I plugged in the mass, which was 200 grams. I solved that k must be 2.5. So if k is 2.5, r must be 1 over 2.5, which is 0.4.
So are we 0.4 centimeters? Unfortunately, we're only about 0.3. So there's some error here. But we saw that in our graph that there seemed to be quite a bit in error. Despite that error, I think our experiment tells us two very important things, which are summarized by this equation on the right. Sigma f equals ma. A is partly going to depend on the square of velocity. We got that from the quadratic graph. And partly going to depend on the inverse length of the rope that we have here. That means that A must be v squared over r. And we can use that anytime something is moving with a centripetal acceleration.